Hello, we are back here, and I'm gonna quickly review what's the status here of the course for you. And here is the syllabus. Okay, and you know that's we want to concentrate on the schedule here. Note, see that the first partial exam was on March 6th, and it started at 7 a.m. Okay, the second exam is going to be on April 17th, after the spring break. It's also going to start at 7 a.m. on the 17th of April. We will end the following day, okay? And we can note, see also, here you go. Third exam is the 15th of May, ends at the 7 a.m. of the following day. And note, see that the final exam starts on the 30th of May. It's not a 7 a.m. It's a 7:30 a.m. Okay, so you have your 24-hour windows a little bit later. I changed it to ensure that we are in agreement with the schedule of the final exams with the college. If you go to the college website, for instance, you see that their schedule of final exam, starts on 7:30 a.m. on the 30th of May. Here is the course catalog, the schedule of classes, spring 2023. Okay, and go from February 6th to June 5th. And let's take a look. If you go down, if you scroll down, you're going to see the schedule of the final exams, final exam date and time. If the classes meet, on those days, Monday and Wednesday, right? Which is not our case. We don't have a set schedule, so we have to pick up a date, anywhere between the earliest date of the final exam is scheduled and the latest date of the final exam is scheduled. So you can see that the earliest day here would be May 30th. Okay, May 30th, and the earliest time is 7:30. So I'm scheduling the final exam according to this date, 7:30, May 30th. Initially I had scheduled for the 29th, but I had to change that to reflect the fact that we must schedule it within that week of finals published by the college. Okay, that is for the exams. We had, here you go, we are a little bit behind. We are in the week of the 20th. So I'm recording this capacitance video here for you. I have, last year I recorded a capacitance class like this one, but for some reason my recording doesn't show the screen, only shows my voice, my voice recording, so I have to record that from scratch. If you go to my website, my YouTube channel, let's go there, my YouTube channel. Go. You're going to see that there is a bunch of videos that I recorded and I uploaded to my channel. If you want to get ahead of the schedule here, you might want to go to this page of mine. Notice that I have physics 7, right? Physics 7 again. Well, you don't want to bother about physics 7, but here are the videos for the physics 38 that I recorded this semester. But if you keep upon going down, physics 7, physics 6, what is physics 6? In November of 2000, in the fall of 2022, I recorded videos for the physics 6 course that I was teaching. You don't want to bother with that either. you want to look for my Physics 38 video of last spring. See, here is my Physics 39 video that I taught in the summer. You don't want to bother with that, but you want to look at those videos, Physics 38. This one, for instance, 21st of April 2022, 19th of April 2022, and so on, right? So if you want to get ahead of the schedule, you might want to take a look at those Physics 38 videos that I taught back in the spring of 2022. Every now and then I'm gonna look at those videos here and I'm gonna post there in the Canvas, in the site of our Canvas course. And here is the Canvas course. Those are the notes. And here are the video links for the classes. Okay, chapters 21 and 22 is in this video right here. Chapter 23, Gauss's law, is in this video here. Chapter 24, electric potential. 24 and 25, electric potential and capacitors. I mixed up in I combined them in this single video. And this here is an older version. It's not the most recent one, so it's one of those videos that you saw that I recorded back in the spring of 2022. Here's the first part of capacitors, okay, and here also an older version, capacitance and capacitors, older version. And today we are going to record the newest version because there is a problem with one of those recordings, that the images, the screen sharing that I was doing for some reason didn't show up there. Okay. Okay, and I also want to point out that you already have homework 5 and 6 for capacitors and current and resistance. Okay. I am scheduling those. This one is supposed to be scheduled for May 30th. Okay, I'm gonna correct that for you, so you have the proper due date. And now I have here again homework 1, 2, 3, 4, 5, and 6. Okay, starting with homework 4, I'm giving you until the end of the course to finish them. Okay, I posted homework 4, 5, and 6. We are covering the material for homework 5 today. And the material is right here. Electric potential was covered in that other video that I posted. And we will be covering all this material today. Capacitance, calculating the capacitance, capacitors in parallel and in series, energy stored in an electric field, capacitor with a dielectric, and dielectric and Gauss's law. And what do you want to know about capacitor? So let's talk about what is a capacitor. Okay? There are all sorts of capacitors. I'm going to illustrate here how a generic capacitor looks like. A generic capacitor is just two pieces of metal that are insulated from each other, electrically insulated from each other. By electrically insulated, we must have a dielectric between them. They cannot be in contact with each other. They cannot be in electrical contact. Remember, it's not that they cannot be in physical contact. They cannot be in electric contact, either with each other or with another device. Okay? When I put this rod here, this line here, is to represent a rod made of a dielectric material. When you have this piece of metal, completely surrounded by a dielectric material, we have that the capacitor is electrically insulated. Okay, is not in electrical contact with anything else, because you have a dielectric material that does not allow the electrons to flow from the metal. Here we have the same thing. That's what a generic capacitor is all about. Once you have this idea of a generic capacitor, you can come up with some specific capacitors. For instance, oh, here you go. Okay, going back to the generic capacitor, right? What you saw here is a generic capacitor that is uncharged. It has no charge whatsoever. It's still considered a capacitor. It still has some potential energy. It still has some capacitance associated with it, but it does not have any energy whatsoever because it is uncharged. Okay, this device becomes a useful device when you charge this device. When you charge, one piece of metal is a plus Q charge and the other piece of metal is a minus Q charge. The charges must be the same, but with opposite sign. When you have the metals charged, electrically charged, there will be an electric potential difference between them. Okay? And that's where the definition of capacitance, which is a quantitative description of a given capacitor, comes about. Okay? Capacitance is a quantity associated with a capacitor, and it is defined as the amount of charge divided by the amount of electric potential. That's how we define capacitance. The unit of capacitance is going to be the unit of Coulomb divided by the unit of voltage. The unit of Coulomb, or the unit of charge is the Coulomb. The unit of voltage is joules per Coulomb. You get Coulomb squared over Joule. This unit shows up so frequently that we call it a farad, represented by the letter F. Now, before we proceed, think about that. Why do we study capacitor? Okay, the reason we study capacitor is because of this little paragraph that you see here. In electricity, magnetism, and electronics, there are 4 basic devices. Capacitors is one of them. And then you'll have 3 other devices that we're going to study. Not all of them, but we're going to study resistors, we're going to study inductors. And there is this 4th device, that's a recent one that was invented recently, is the transistor. We are not going to cover transistors in this course, but we are going to cover all those 3 devices here in this course. So that's why we study capacitors and capacitance, because it's one of the 4 basic devices in electricity, magnetism, and electronics. You can combine those 4 devices in several different ways to produce whatever you want. Your cell phone is a combination of capacitors, resistors, inductors, and transistors. Your TV, your display monitor is also a combination of those 4 devices, and so on. Okay. Now, going back here to the definition of capacitance, is charge over voltage. Remember this definition. We're going to be using it throughout this chapter. And so let's do a simple numerical example. Suppose that we go ahead, get the 2 pieces of metal, charge them to 1 microcoulomb. One is a plus 1 microcoulomb, the other one is minus 1 microcoulomb, and we keep them at electric potential of 10 volts. Okay, you can do that. How do you do that? You can do that by connecting this device here to a battery. Okay, you can get a battery between those 2 devices, and the battery is going to charge your metal plates, and not only you're going to charge, but it's going to keep them at a given electric potential difference. Okay, so what would be the capacitance of this device? Okay, 10 to minus 4 farad, or 0.1 millifarad. What you see there in the book, is all sorts of capacitors that you can find out there. This is a cylindrical capacitor. Those are all cylindrical capacitors. Those are planar capacitors, and I'm going to show you how they look like. This is another planar capacitor, and they are sold out there. Those things cost anywhere between 10 cents all the way up to $10, $20, $30, depending on the capacitor. You can even go into here, do a Google search, capacitors, right? I like the Wikipedia, and they are also going to have a picture of several different capacitors that you may have. They even have the history of capacitors. Okay, capacitors were initially called Leyden jars. Benjamin Franklin worked with capacitors, investigated the Leyden jar, okay, and came to the conclusion that the charge was stored on the glass, not in the water, and others had assumed. Okay, yeah. And 17 is a device that, as far back as 1745. Okay, he found that charge could be stored by connecting a high voltage electrostatic generator by a wire to a volume of water in a handheld glass jar. Okay, just not exactly with the capacitor that we have today, but it's close enough. Here, I like this illustration of the capacitor. This is just one possible type of capacitor. This is the parallel plate capacitor. We already studied how the electric field behaves between those two plates, right? So what we have here, we can charge this device by connecting it to a battery. One is going to be positively charged, the other is going to be negatively charged. You're going to have an electric field between those two plates, an electric potential difference as well. And you saw before that the electric field is going to be uniformly charged here, right? It's going to be a uniform electric field here. And this is a capacitor that you can change the distance between the plates. Okay, it's a capacitor that has a variable capacitance because you can change the distance between the plates. And that's where we come to the point where I want to talk about some specific capacitors, specific types of capacitors. Here you go. Here's the generic type of capacitor. You already know how to charge them with a battery, and here you go. Here's another example of a capacitor. The parallel plate capacitor, which is exactly that illustration that you saw here. Parallel plate capacitor with a uniform electric field between those two plates. Again, why it's important? Because this type of device can store electric energy, provided it is charged, provided there is a charge. If you discharge this capacitor, there won't be any electric potential energy whatsoever. Here's another example of a capacitor. It's a spherical capacitor with two concentric spheres electrically charged. The inner sphere can be also positive and the outer negative, just like in this illustration. Okay, it's still a capacitor. Here's another example of another capacitor, the cylindrical capacitor. In all those cases, you know what is the behavior of the electric field, because we calculated that not just the electric field between those two plates, right? But the electric potential as well. We did that in the previous chapters. You know that the electric field of this configuration is a uniform electric field. You know that the electric field of this configuration is going to be a zero electric field here inside and a zero electric field outside, according to Gauss's law. And the electric field will be restricted only to this region here in between, which has a dielectric. Air, for instance, is a type of dielectric. The same thing here for our cylindrical capacitor. We also calculated what's the electric field between those two cylindrical surfaces. So with the electric field, we can calculate the electric potential difference, right? The inner cylinder in this case has a radius A, the outer cylinder has a radius B. You can calculate the electric potential difference, and from the electric potential difference, you can calculate the capacitance as well. And we are going to do that in this course. We are going to do that today. Okay, here is the parallel plate capacitor, and here is the symbol of the capacitor. Okay, so we represent a capacitor in every circuit diagram. We represent a capacitor as two parallel plates. Okay, two lines like that. That's one of the representation of the capacitors. There are others, okay, but this one is the most commonly used. If you go to Wikipedia, you're going to see that there are other representations of a capacitor. Here you go. This is a fixed capacitor that used mostly of the time, and this one is the polarized capacitor. There are capacitors that are polarized. Both, those most capacitors out there, they are not polarized, but there are a few out there that you must be careful that they are polarized. And then we have the variable capacitor. Variable capacitor with this arrow here to indicate that you can tune the capacitance of the capacitor. What you see right in here is a variable capacitor because you can change the distances between the plates. Okay, but this is just a quick review of how capacitor is, and we're gonna go into the details, into the mathematical details of the capacitor. Okay, and here's the example. Okay, and here you go. Consider that our first example of capacitor, example 1. Planar capacitor. Two metallic discs of same size form a capacitor. Two metallic discs, just like you saw here in Wikipedia. One metallic disc, another metallic disc. Everything else that you see here is supposed to electrically insulate my capacitor from the surrounding environment. So here inside, even though it looks like it's a metal, inside this metal, there must be a dielectric here to electrically insulate the capacitor, okay? Two metallic discs of same size form a capacitor. If the two discs are separated by a distance d and each have an area A, find their capacitance. The dielectric between them is between the two discs is air, which by the way is a dielectric. Okay, so what do? We start with the definition of capacitance, Q divided by V, and then we want to find out what's going to be the electric potential between the two plates, right? You remember, if you don't remember, if you didn't memorize by heart what's the potential difference between the two, it's very easy to remember that for this specific case, the electric field is going to be uniform, right? And we calculated that this uniform electric field is the charge density, surface charge density, divided by this constant epsilon naught. And don't forget that the generic relation between the electric field and the electric potential is minus dV dx. Okay? The first thing that we want to do, we want to change the sigma in terms of charge, right? So when we substitute right in here for the V, we will be able to cancel out. But so let's write our electric field in terms of Q, right? And that's what we get. You might want to write it in terms of the radius of the capacitor. Area is pi r squared. And then we go the next step to find out the potential difference between them, between those two plates. Okay, you know that if you solve this differential equation, you do get that the potential difference between the capacitor, between the plate of the capacitor, is going to be like E times X, right? E times X. But we want to know the potential difference between each plate, not between one plate and somewhere within those devices. So what do? We replace the X by the letter D, by the distance between the capacitor. And now that we have the V, we can substitute right in there. And then what's going to happen? The Q that you have upstairs is going to cancel out with the Q that you have downstairs. And we are going to get a capacitance for the parallel plate equal to this equation here, epsilon naught A over D. One thing that's very important, even though the capacitance is defined in terms of Q and V, the final result of the capacitance for any capacitor is not going to be dependent on Q, neither on V. Why is that? Because the V is always proportional to the charge. and this Q is always going to be canceled out. And what you end up having at the end is going to be a function only of the geometric characteristics of the capacitor. Area is a geometric characteristic of the capacitor. The distance between the plates is a geometric characteristic of the capacitor. And epsilon naught is a universal constant. That's the capacitance for 2. That is the capacitance of a parallel plate capacitor. Okay? And what is important? This equation applies to any geometry of a flat capacitor. Whether it's a circular capacitor, whether it's a square capacitor, whether it's a rectangular capacitor, whether it's a triangular capacitor. As I mentioned before, the capacitance does not depend. Also notice that for this specific case, the capacitance does not depend on the charge nor on the voltage, but only the geometrical parameters of the device. This characteristic also applies to other geometrical configurations of the capacitor, whether it is spherical, whether it is spherical capacitor, whether it is cylindrical capacitor, etc. Okay, and that's what I have here. Okay, so let's summarize how you find the capacitance of a capacitor. First, we calculate the electric field. Then we determine the electric potential difference between the two conductors, right? Two conductors of the capacitor. Then you simplify your equation to obtain an expression that's a function of the geometrical parameters of the device. Those are the 3 steps that you have to follow to find the capacitance. First, we calculate the electric field, then determine the electric potential difference. Okay, and then what else? Use the definition of capacitance, which is Q over V, and simplify your equation to obtain an expression that's a function of the geometrical parameters of the device. We will repeat this procedure for the other capacitors, like the spherical, the cylindrical, concentric capacitors. Both are concentric. If they're not concentric, it's a problem a little bit more difficult to calculate. Okay? So we start with the spherical concentric capacitor. Okay? The illustration is that one that you saw initially. Here you go. Those are 2 spheres of radius A and radius B. Okay, and we go ahead and solve, spell down the capacitance equation. VA minus VB. VA minus VB is, electric potential of the surface minus the electric potential of this surface. Okay, you do know that this type of device, this type of charger device, behaves just like a point charge, right? Within this volume. That's what we saw before. So the electric potential of this sphere here at the surface of the sphere is going to be given by KQ divided by A. Okay? KQ divided by A. And that's what I have here. For the outer sphere, is going to be also KQ divided by B. And we go ahead and substitute right here in this equation. That's what I did here. The Q is going to cancel out. And like before, we are going to have an expression that's going to be a function only of the geometric parameters of the capacitor plus this universal constant that's K, which can be written as 4 pi epsilon naught. Okay? And that's the capacitance of the spherical capacitor. We repeat that. Here you go. Here's going to be my example 2. Now, example 3. Find the capacitance per unit of length of two cylindrical concentric charges that are uniformly distributed. Going back here, you go. That's how it looks like, the cylindrical capacitor. A charged inner cylinder surrounded by another cylinder of larger radius. Those are the radii. Recall that we solved the electric field for this type of configuration. In this type of configuration, using Gauss's law, you know that the electric field here inside is 0 because there is no electric charge inducing this volume. And we also know that the electric field outside this volume is also 0, right? Giving us a non-zero electric field in this region. What was the result when you calculate that? Okay, the result was something like that. The electric field was the surface charge density times the inner radius, the radius of the inner cylinder, divided by a constant epsilon naught r. Okay? From this equation here, you can find out what's going to be the electric potential difference between the surface B, the larger surface, and the smaller surface. Okay? E dot dr, right? We substitute the E right in here, and we have this integrand that you know how to take the integral. It's going to be the log of r. Everything else here is going to be a constant. Log of B over A, and that's the electric potential difference that goes right here into this equation. But let's not forget that the sigma is a function of the charge, right? Here you go. Sigma is going to be Q divided by A, capital A for area, lowercase a for the radius, log epsilon naught log B over A. Okay, Q, just like before, cancel out this Q. For the sake of this course, remember the electric potential difference will always be proportional to the electric charge. That's why you end up having no charge or voltage in the equation, but only the geometrical parameters of the capacitor. Where did I get this L? Where did I get this L? Okay, this L here, which is the length of the capacitor, came from the area, 2 pi r times L. So what they're asking is not the capacitance, but the capacitance per unit of length. In order to get the capacitance per unit of length, you just pass the L to the other side and you get this expression for the capacitance per unit of length. Okay? So, summary, definition of capacitor, how a capacitor looks like, right? Two metal what is a capacitor? Is two conductors electrically insulated. And then we go for the definition of capacitance. And then we did the capacitance for a planar capacitor, a spherical capacitor, and a cylindrical capacitor. What you're going to see next, what happens when you connect capacitors with each other.